Good morning, everyone. This is Dr. Ramakrishna. We have seen in the session 3 about how to create arrays and then how to use NumPy to perform basic operations on multi-dimensional arrays. Let us continue to it, and let's also see how we can compute different operations on NumPy arrays using universal functions concept. In Python, a universal function is a function that operates elements wise on n-dimensional arrays, which are multi-dimensional arrays in NumPy. NumPy provides a set of universal functions that are optimized for performance and can operate on n-dimensional array of any size and any shape. These functions are implemented in C or Fortran, and they are faster than equivalent Python functions normally used on a sequential data, because they avoid the overhead of interpreting Python code. The biggest advantage of the universal functions is a faster performance when compared to the normal functions used on any sequential data. And we all know the operations can be done on numeric data or addition, subtraction, multiplication, division, and so on. But whereas using the same operations using normal Python functions and using universal functions under NumPy are completely unique. And these are some examples of universal functions in NumPy. np.add, and you will provide two arguments, x1 and x2 are two different arrays, and it adds the two arrays element by element. Similarly, np.subtract x1 comma x2 subtracts two arrays element wise. np.multiply will multiply two array elements of x1 and x2 arrays. np.divide of x1 comma x2 divides two array elements to two arrays element by element. Similarly, the other functions like exponential, logarithmic, trigonometric functions also possible. We'll explore all these functions in this section. Computation on NumPy arrays can be very fast or it can be very slow. The key to make it fast is to use vectorized operations, generally implemented through NumPy universal functions. This section motivates the need for NumPy universal functions, which can be used to make repeated calculations on array elements much more efficient. It introduces many of the most common and useful arithmetic universal functions available in NumPy package. Let us see, using math library, let us see how this square root of any element works. Just I import math, and then x equal to 9, and then where y equal to square root of x. And now you observe, this is how simple it is to calculate the square root of x using a normal math square root function, right? But the time taken to calculate the square root of x is a bit higher than the use of same square root of x in universal function. Now let us see. Let's create an array of 10 elements with an empty function. I already told you empty function comes with the uninitialization. These are the 10 values created uninitialized way by empty function. So let's create an array of values and then calculate the reciprocal value of every element of an array and see how much time it takes usually by a Python interpreter. Now I just took import NumPy as an NP and then I set the seed is 0, where you all know the seed will help us to set the value which help to reproduce the similar random values on every run. So I am just defining a new function to calculate the reciprocal value of every element of an array. You can just define the name of the function is compute reciprocal. And the values is list of values or the array of values. I just wanted to find the output in an output. So this NumPy empty function, as I told you, it helps us to create an NumPy array with a specified shape and data type uninitialized way with the random values. So as we all know, the reciprocal of any element is 1 by itself. And I wanted to just calculate the reciprocal value of every element of an array, for which I required a for loop to navigate to each and every element of an array. So for that, here is a code snippet for I in range of the length of values, that's the size of the array, and then output of I is equal to 1 by the corresponding value. So after calculating the reciprocals of every element of an array values, I just return the output array called output. The whole purpose of writing this is how normally it is calculated the reciprocal values using loops. And here I am just calling a compute reciprocal by passing an array by generating 5 elements between 1 to 10. So let's run this code. Now you see the random values between 1 to 10 are 6, 1, 4, 4, 8, 5 elements. And then after finding the reciprocal values of those corresponding elements in an array, you got the reciprocal of 6 is 0.16 or something like, so 1 by 1 is 1. Right, you observe you have got all the reciprocal values of every element of an array values. But you see the output is float values. Now, for suppose if you wanted to know how much time it took to run the code snippet compute reciprocals of values, you can just use percentile timing. You can observe here this reciprocal calculation of every element of an array took on an average 35.8 microseconds with a standard deviation of 2.63 microseconds per loop. That means totally it had 7 runs with every 10,000 loops. So for each 10,000 loops repeated for 7 times, on an average it took 35.8 microseconds with a standard deviation of 2.63 microseconds. Let us see the time taken by the universal function will be less. So this implementation probably feels fairly natural to some one from, says usually when you come from the programming experience in C language or Java, usually we do like this. But whereas coming to the Python practitioners, you can see how it works. So what I'm doing is, on a simple 5 elements, calculation of reciprocal values is pretty easy. But when you work with a bigger size arrays, it takes more time. Say, the time it took is here running compute reciprocals of big array takes an average of 58.5 microseconds per loop with a standard deviation of 3.57 microseconds, and it was run 7 times with 10,000 loops each time. Right. It takes several seconds or microseconds to compute these million operations and to store the result. If we were working in compiled code instead of this code, see, we have written the complete code and working on it. That's the reason why it is taking more time. Instead of it, if we work in compiled code instead, this type specification would be known before the code executes, and the result could be computed much more efficiently. That's where there is a concept called universal functions in NumPy array library in Python. For many types of operations, NumPy provides a convenient interface into just this kind of a statically typed compiled routine. This is known as vectorized operation. This can be accomplished by simply performing an operation on the array, which will then be applied to each element of an array. This vectorized approach is designed to push the loop into the compiled layer that underlines NumPy, leading to much faster execution. That's how we can improve the performance of running a code snippet using universal function. Now let us once compare how it runs and then how it takes it. Now these both are same, right? Now if I try to run it, now you observe the time taken by the compute reciprocals of values or directly running finding the reciprocal. Now you observe carefully, the second one took very less time to run the code snippet one by values, right? This is what is called vectorized operation. So we have more user-friendly universal functions to further improve the performance of running a code snippet using NumPy library. Let us take, for an example, let's take you can just calculate the one dimensional array to the multi-dimensional array, right? And then universal function operations are not limited to one-dimensional arrays. We can also act on multi-dimensional arrays as well. Now you can see, first suppose if I wanted to add a scalar value to an array of elements 3 by 3 matrix. So my 3 by 3 matrix is 0 to 8 arranged in 3 by 3 shape. And I just added 2 to the every element. As I told you, universal function addition. So plus symbol is an alias of add. This is same as np dot add of x comma 2. Right? So this plus symbol is an alias of addition or add universal function in NumPy library. Now you see, as I told you, universal functions helps us to perform the set operation on every element of an array. Though the dimension is different, here x is a vectorized array, whereas 2 is the scalar, and I can treat it as a two-dimensional and one-dimensional. Still, it is possible to perform add operation. So, computations using vectorization through universal functions are nearly always more efficient than their counterpart implementation using normal Python loops, especially as the arrays grows in size. Anytime you see that a particular loop in a Python script, you should consider whether it can be replaced with a vectorized expression or not. That is the key of improving the speed of calculation. Universal functions exist in two flavors in NumPy library. One is a unary functions and the second one is a binary function. Both are possible. When you have a one vectorized array as an input, it's called unary. And whereas if you have two vectorized arrays as an inputs to a function, it's called as a binary function. Let us explore the regular arithmetic operations through NumPy universal functions. These are quite natural in our day-to-day calculations to analyze the data. Python's native arithmetic operators like plus, minus, star, divide, percentile, all these are naturally used. These are all considered as the aliasing to the corresponding universal functions in NumPy library. Just have a look of this code snippet where I wanted to perform the addition using plus, subtraction using a minus, multiplication using star, asterisk, and divide using symbol, and then of course double slash indicates that it returns a coefficient. Okay, and whereas a percentile acts as a modulus operator. Now you got your resultant arrays here after performing these universal functions. Of course, we have the other natural symbols to perform the exponential and the division. And you can also use a sine operator minus that will helps to negate every element of an array. This is how you can just calculate the negation. Here it's not the negation, I mean, it's not the complement, but it's only sine negation. And then x power 2 and x modulus of 2. In addition, these can be strung together however you wish. And the standard order of operations is respected. You all know the standard order of operation follows order of precedence of arithmetic operators. Like if you have exponential, right? So in total, if you consider, it takes the bracket sub expression into a first priority, followed by exponential operation, of course negation, exponential operation, and then your multiplication and division, addition and subtraction, and the evaluation of expression always follows right to left order with the order of precedence for these operators. So that will be respected or followed when it's performing an expressions with different operators. You can see the simply how the universal expression add can be used. Okay. Here are the list of various arithmetic operators and the corresponding universal functions in NumPy, as we have already seen. These are the corresponding functions. Now, to find the absolute value of any element of an array, we use a natural absolute function ABS. So, it gives us the absolute value by taking a mod operation. All right. Whereas the corresponding NumPy universal function, np absolute, which is also available under the alias of np.abs, we can simply use np.absolute instead of a natural absolute function abs of x. Of course, the result is same, but what is different? The speed of calculation is different in using the natural absolute function and absolute universal function of a NumPy library. Now you observe the time taken is quite impressive for our universal functions. You can also apply on complex numbers. When we apply this absolute universal function on complex arrays, it takes the quantities of real values, isn't it? We can also apply various trigonometric functions using NumPy library. The NumPy provides a large number of useful universal functions, and some of the most useful, the data scientists, and they use these trigonometric functions. You can also see defining an array of angles using these trigonometric functions. Now, I just took a few theta values by creating an array of elements, an array of 3 elements, with the help of a linear space function where it generates the set size of elements between 0 to pi. Whereas pi is a 3.14 and so on. Between 0 to 3.142, it generates 3 equidistance values. Now we can compute some trigonometric functions on these values. Now I took the theta matrix. Now when I apply np dot sin of theta, it will measure the sinusoidal values of every element of a theta matrix. Similarly, np dot cosine, np dot tan also possible. Now you see these are the corresponding trigonometric values when you apply np dot sin, np dot cos, np dot tan. See, usually we know the sin 90 is 1, but whereas the actual value is 0.89399 and so on. The values are computed to within machine precision, which is why values that should be 0 do not always hit exactly 0. 0 is not exactly the 0. You can see sine 0. In sine theta, you can see the first one is sine 0, but it's not exactly the 0. It is a 0 with a machine precision. Inverse trigonometric functions are also possible with functions like np.arc sine. That's what inverse of sine. np.arc cos. Okay, inverse of arc. Inverse of tan is arc tan. Not only trigonometric functions you can apply in NumPy using universal functions. You also have the scientific functions like finding exponential values and logarithmic values. Another common type of operations available in NumPy universal functions are the exponentials. You can find the exponential of x and the exponential of x power 2. And then, of course, for any number, you can simply use np dot power of the number comma x. Now you can see one thing clearly here is all these universal functions applied on every element of an array. The inverse of the exponentials, the algorithmics, the logarithmics are also available. The basic log gives the natural logarithmic value. If you prefer to compute the base 2 logarithmic or the base 10 logarithmic are also possible using universal functions. Here you can see how we can use the natural logarithmic values of any array or the base 2 logarithmic of an array or base 10 logarithmic of an array. As I said, it can be applied on one-dimensional or multi-dimensional. This is not only limited to it, you have the different versions of useful logarithmic and exponential universal functions. Those maintains the scientific precision values. Here are two universal functions available to measure the scientific precisions, right? So when x is very small, these functions gives more precise values than if the raw natural, logarithmic, or exponential universal functions. So there are specialized universal functions. NumPy has many more universal functions available, including hyperbolic trigonometric functions, bitwise arithmetic operations, comparison operators, conversions from radians to degrees, rounding and remainders, and much more. Look through the NumPy documentation, reveals a lot of interesting functionalities. I recommend the participants to go through the sci-fi library. Of course, we will be studying the sci-fi library in the upcoming sessions. Right? I'll limit my discussion up to here about our universal functions in NumPy library. So simply to say, the universal functions will help us to speed up the calculation when we are applying various operations on a bigger data, right? So thank you very much. We'll see the more features of NumPy in upcoming session.